Good afternoon, everyone. My name is Erich Haratsch. I'm a senior director at Marvell, where I lead the storage architecture team. And it is my pleasure to speak here about storage devices for the AI data center here at the SDC conference in Denver. Okay, so here's the outline for my talk. So I'll just give a brief introduction of the evolution of AI. I'll talk about the complexity of AI models. I'll rehash a bit the AI data processing pipeline that Curtis talked about in detail earlier in the morning. I will then talk about storage in the AI data center, about performance considerations for storage, in particular for SSDs, and then I will conclude my talk. So here I'm trying to summarize the recent development of AI. I would say that kind of the current efforts in AI, they really started in 2012 when a new model came out, AlexNet. This model was able to have much better accuracy in image recognition than what could be achieved before. And this really showed to the world that AI works. And I think this really started a tremendous efforts in terms of first research and development for AI. Back then, deep learning algorithms were used. The primary use case were image and speech recognition. Then in 2016, a new method was introduced, transformers. They first were used for recommendation models, but also for text-based prediction models like GPT-2. And then this led the way towards the new generative AI algorithms. And ChatGPT in 2022 really showed the world then how powerful AI can be. And I think it really jump-started a huge investment in the industry to build AI data centers. And since then, almost every year, new models coming out. And I'm trying to summarize some new developments. So the first thing is that the industry went from text-based AI models to multimodal models that also include images and videos for training and then also for generation. Then a new concept is also reasoning and chain of thought. So the idea here is really to break up complex tasks into multiple steps. And then the AI model then really works through these tasks step by step in a reasoning fashion, similar to human beings. And then also another new type of model are so-called world foundation models. So these are really models that try to capture the world, especially for robots and for humanoids. And this leads to new applications then in terms of physical AI. So an example for a world foundation model is the Cosmos model that was introduced by NVIDIA this year. So as you can see here, the complexity of the models, the capabilities of the models, they keep increasing. And this also means that the compute memory and the storage requirements continue to increase, especially also when we talk about reasoning models, physical AI models. It does lead to an increase in terms of parameters, tokens, data sizes that need to be dealt with. So that has, of course, also implications for storage. So I want to summarize here a little bit the complexity of AI models. I want to put numbers behind some exemplary models. I'll start with AlexNet that was introduced in 2012. So that model had a parameter count of about 60 million. So if you assume 4 bytes per parameter, you could store that model in about 240 megabytes. And then it was reported that it was trained using 1.2 terabytes of raw data. Then GPT-3, this transformer-based generative AI model, was a big step forward in terms of complexity. So the number of parameters increased to 175 billion. That corresponds to a model size of 700 gigabytes. And it has been reported that it was trained on 45 terabytes of data. Then when we talk about GPT-4, it had an increase by a factor of 10x, 1.76 trillion parameters. The model size, 7 terabytes, and it has been estimated that this model was trained on 1 petabytes of data. So for comparison, I'm also showing other models by Meta, Llama 2 and Llama 3. I mean, they stand out in the sense that they're open source. And you can see here that in terms of parameter counts and model size, they scale accordingly. And newer models have even more. So you can see the parameter count is increasing, but also the data that is being trained on also keeps increasing. The goal, of course, is to store the model in memory, but the training data, of course, cannot be stored in memory. It needs to be stored in storage and needs to be brought to the AI compute then for training and inference. So here's a quick recap of the AI processing phases and what it means in terms of the storage workloads. I don't want to repeat what Curtis said earlier, but just, I guess, for those who missed the earlier talk, these are the phases. First there's data ingestion, to collect all the data, make it available. So we're talking here about petabytes of data. The random accesses are typically sequential. Then there's a data preparation phase. So this involves filtering. This involves tokenization of the data. Accesses here are sequential, also random. And the data sizes that are being worked on from a storage perspective are in the range of terabytes. Then for training, it can be sequential and random. And the sequential aspect really comes due to the fact that data is being checkpointed. The model state needs to be saved from time to time because these AI model periods run for a very long time on many GPUs. If something fails, you don't want to lose the state. So that's why checkpointing is very important. It's important to save the model state to storage, and that happens in a sequential manner. But there are also random data accesses within training. And within, in terms of the local accesses for storage, we're talking about gigabytes. Then for inference, the random accesses are really dominant. So the data size accesses increase here again to terabytes. And then in the end, the training results, but also the inference results need to be archived. And here we're talking then again about petabytes of data of storage, and the accesses are typically sequential. Okay, I wanted to talk about training versus inference. So training, to summarize it in a simplified manner, essentially it's one large job to train the model, which is running on a supercomputer with 10,000s or 100,000s of GPUs that are all connected with each other. The industry is even talking about now moving towards 1 million GPU clusters in the AI data center. What is important here is bandwidth, to get the job done in a reasonable amount of time. These jobs can run over weeks, months. And a key aspect from a storage perspective here is the checkpointing to save the model state into storage. Inference is different. So inference, especially when we talk about inference in a data center at scale, with millions or billions of users asking questions. So here we're talking about really many thousands of jobs running in parallel. A key metric here is really latency, the time to answer. Latency here is the key metric. And then there's also a technique being used in terms for inference, retrieval augmented generation. It essentially means that additional large amounts of data sets are being used to increase the accuracy of the inference results. And that drives additional need for storage. So, I wanted to talk here about hardware, about storage devices. So here, from that perspective, I want to show an exemplary, compute node, consisting of compute trays within a compute rack So let's start here first on the left side with the AI compute tray or AI compute server. So when you look at a recent platform, the NVIDIA GB200 system, which is a 72 GPU system. So how does it all up to 72 GPUs, and what's the role of storage here? So within a compute tray, essentially you have two super chips where each super chip has two GPUs. It has also high bandwidth memory. You also have two CPUs and also DRAM then within the compute tray, data processing units, and then here's storage. You have here in this configuration here, you have here 8 E1.S drives within one compute tray. And then also you need to have connectivity to the outside in terms of NICs. So when we look here at bandwidth, so first of all, the computational speed, when we talk about the GPUs, we're talking about teraflops, even 1 petaflop in terms of the processing speed. The bandwidth towards the HBM memories, we're talking about terabytes per second. And we all know about the speed of SSDs, where you're talking about gigabytes per second, dozens of gigabytes per second. And you can really see here in terms of storage really being the slowest component in the overall system. And when we talk now about training, but also inference, you don't want these GPUs, of course, to be idle. So that's why there's a lot of interest now to increase the performance of the SSDs. So when we now look at one compute rack, in this system here, so what does it look like? So you have a total of 18 compute trays. I showed the compute tray here. And then also you have 9 switch trays to, for the connectivity between the compute trays within a compute rack. This is also called the scale-up network, where it's all about low latency and high speed. So let's go back to storage. When we talk about storage, there are 16 PCIe lanes per superchip that are dedicated for storage. So when 16 lanes, each SSD has 4 lanes. So you can connect up to 4 SSDs per GPU superchip. And because you have two superchips, that's why you end up here with 8 SSDs. So you have 8 SSDs, here in a E1.S form factor per compute tray. You have a total of 18 compute trays. So in total, you can have up to 144 E1.S drives per AI compute rack. And it doesn't have to be E1.S. There are also configurations with U.2 drives, for example. Okay, so let's talk about the AI storage tiers. So you have the compute rack that I just talked about, but then you also have external storage. First of all, you have a performance storage tier, so typically consisting of SSDs and then an object storage tier, which can have either SSDs or HDDs. They are connected to the AI compute rack, using fiber cables and usually using Ethernet or InfiniBand. I wanted to say here that TLC NAND flash is typically used for the compute racks and also for the performance storage tier, and then QLC or even hard disk drives are used in the object storage tier. So in the past, SSDs adopted next generation PCI interfaces usually later than CPUs, because not as much performance was needed. There was more emphasis on power. And whereas now with AI, as explained earlier, storage is really the slowest link in this whole processing pipeline. So AI is really now driving the adoption of next generation PCIe SSDs. So there's a lot of interest now, for example, in Gen 6 SSDs for AI. SSDs typically were designed to saturate sequential and 4K byte random read performance. However, in AI workloads, and especially when we talk about inference, they have random accesses that are smaller than 4K bytes, much smaller than 4K bytes. And current SSDs are not optimized really for random read workloads with accesses smaller than 4 KB. This is the reason why NVIDIA started a Storage Next initiative. CJ Newbern and his colleagues at NVIDIA, they presented the Storage Next initiative at the Supercompute and OCP conferences last year and also at the GTC conference this year. And NVIDIA is really asking for 200 million IOPS performance for 512 bytes for 16 PCIe lanes. And how do they get to that number? So when we, as I said before, there are 16 PCIe lanes that are kind of dedicated to storage per GPU superchip. So that corresponds to a raw bandwidth of 128 gigabytes per second. So in practice, because of overhead that you have in the protocols and interfaces, this comes down to 110 gigabytes per second for 16 lanes. When you then convert that into 4 KB random read performance, the best you could get is about 27 million IOPS. And then when you look at 512-byte accesses, you have to multiply that by a number of 8, so 215 million IOPS. So that's where the 200 million IOPS comes from. So what does it mean in terms of a 4-lane PCIe SSD? So the raw bandwidth for Gen 6 is 32 gigabytes per second. That's around 27, 28 gigabytes per second effective. And then for 4 KB accesses, that's about 6.7 million IOPS. So typically, an SSD would be designed to reach that target at the maximum. But as I said, for AI, since the accesses are smaller, when we talk about 512-byte accesses, ideally you would have 8 times more IOPS, about 50 million IOPS per SSD. And there's no SSD and even SSD controller that is designed for that type of performance. So what is needed to make this happen? So I'm not offering here a solution, but I'm talking about what the components in the system are that need to be looked at to tackle this problem. So you can see here, first of all, an SSD controller, what it looks like. It has external NAND, external DRAM. It has interfaces towards the host, towards DRAM, towards NAND. There are CPUs that do a lot of this, command processing, the flash translation layer processing. There's a flash controller that does the error correction and also all the interactions with the NAND. And of course, there's the NVMe controller to deal with the NVMe protocol. So in order to improve the performance, to get to 8 times better random read IOPS, these are the things that need to be looked at. First of all, the key thing is to look at the NAND media. Now, right now, TLC and QLC NAND are typically used, but you really want faster read performance. You can achieve that by going to SLC or MLC NAND, 1 bit or 2 bits per cell NAND. That really reduces the read time. Then also what could be looked at is to optimize the page and plane architecture. For example, moving to smaller page sizes, moving towards more planes to improve parallelism, to improve the performance capability of the NAND media. Then on the SSD controller side, a key, of course, everything needs to be scaled up to achieve those performance metrics. But one key thing is really the CPUs, because the CPUs are typically, the performance limit for random read performance. They would need to be scaled up. And also, you could think about having more hardware assist or more hardware acceleration for firmware tasks that are running now in firmware. So you would give up some flexibility, but better performance. Then, of course, the host interface could also be optimized. I mean, there's a question, could there be optimizations in the NVMe protocol to also facilitate these high IOPS SSDs? And then, one key thing is also when we talk about improving random read IOPS by a factor of 8, it will really increase the power, of course, of that whole system, of the controller, of the SSD. So 8 times higher random read performance will increase power, and it will probably need optimizations in terms of the form factors. This may even need new form factors that are able to deal with these higher kind of performance characteristics for SSD storage. So here I conclude then my talk, and I think almost on time. So we have 5 more minutes. And the key point is that new models are coming up, despite, I guess, the confusion that happened when DeepSeek came out, saying that actually AI models are becoming less complex. The opposite is really the case. The AI models, they continue to become more complex. They drive also more demand for compute memory, but also for storage. Storage is an essential component in AI data centers. I remember at the time, 1-2 years ago, everyone was wondering, what's the role of storage in AI? And I hope I showed you there's plenty of storage, even within the compute nodes, but of course also in the external storage nodes. Then I think a key lesson here also is that it's really AI now that is driving the adoption of next generation PCI interfaces for storage. And then when we talk about increasing random read IOPS by a factor of 8, we have to optimize the whole system. We have to look at the NAND media, the SSD controller, the host interfaces, and we also have to talk potentially about new form factors. That's all I had. So thank you for your attention.
Hey, thanks, Erich. Any questions for, we got all kinds of questions. I'll start over here.
You mentioned that inference is driving a requirement for smaller than 4K IOs. Where do you see that? Like in my testing, I don't see smaller than 4K. What's driving, do you think, NVIDIA's requirement for down to 512 byte?
Yeah, it's really on inference, on the different steps that need to be done there. I can not go into the specifics. I mean, I would recommend to look at the NVIDIA presentations from last and this year. And I know you're quite active in the
they're pretty ambiguous too. So I guess I'm asking, does anyone actually have any specific data that is backing up NVIDIA's claim that they need smaller than 4K IOs? That's my question, maybe for the whole group here.
Sounds like a good hallway conversation afterwards here for folks.
Thank you. In terms of checkpointing, we know a lot of that is being stored, or almost all of that is being stored on SSDs, so that it reduces the time to get back up. Do you know if there's a lot of that data that's being archived in any way? So in other words, like all the iterations of the checkpointing, are they being archived onto HDD or anything, or do they just, once the model kind of progresses, do they trash those prior checkpoint?
That's a good question, and I think maybe Curtis, are you maybe, I think, in a better position to answer this type of question?
I'd have to say I don't know the answer to that question for sure. I know that in some of the asynchronous models that there are checkpoints retained for a longer period of time, so that in some cases they need to rewind and replay from a little bit further back. I don't have the information on whether they're archiving those and saving them later. Most of the cases where I've seen the checkpoints are primarily useful during a given run, and at the end of the run, when everything is complete and done, the checkpoints from the middle don't have a lot of value anymore, or usually trashed at the end of the run. There might be applications for archive I'm not aware of.
Thank you.
Yeah.
I think you mentioned optimization, right? And you talked about the optimization of the host interface, and you talked about NVMe optimization, the protocol itself. Could you elaborate a bit more on that?
Yeah, I mean, I guess I didn't want to offer solutions here, but it's more like a call to action, I think, for this whole room to think about what makes sense, especially I think since a lot of people here are also involved in NVMe. Is there anything that could be done within the NVMe interface to facilitate higher random read IOPS? I feel the key, kind of the low-hanging fruits, the high-impact things to look at are, of course, NAND, SSD controller. But I think on the NVMe side, I think it needs more thought, what could be done there to facilitate such high IOPS SSDs.
Just on newer form factors, you know, I know that the EDSFF have power limits for what each slot can handle as well. Is there work underway to come up with better form factors?
Yeah, I don't know if there's work underway I'm not aware of, I guess work being underway to address specifically, you know, such high ops devices. But I can tell you that, you know, even to saturate performance currently, you know, for the common metrics, it is quite challenging for everybody to stick within those, you know, power and thermal limits. And that's why I'm bringing it up here. So this may require, you know, higher limits and also new form factors potentially.
I'm aware of that.
Yeah.
Yeah, and there is continuing form factor discussion going on that I think we're going to see some additional SSD form factors, but nothing I can talk about just yet. I kind of hate to see that. We've got too many now, is kind of my opinion. But okay, back here.
You know, I think some of this is, you know, feeding the GPU, as long as what is the difference between memory and storage to the GPU as long as you're keeping it moving, right? Like as long as you fill that pipe.
Mm-hmm.
I wonder, from your thoughts, do you see CXL playing a role here in the future? Because NVMe inherently is slow for something small, right? Like if you keep going smaller and smaller requests, what are your thoughts on that?
Yeah, I think CXL could play a storage, so that's a good thought, good point. I mean, you know, there are some platforms, like the ones I've shown here, that don't utilize CXL. So then, but you know, CXL could be an option here, you know, to help break that bottleneck that, you know, that gets introduced by storage-only devices. I think also something worth exploring. Yeah.
Other questions? Yep. Okay.
In your earlier slide, you had a slide where it showed the raw data is at the petabyte scale, and then it gets smaller as it gets to the model, maybe gigabytes, and then it starts to go back up. At the last phase, I forget what you called it, but maybe the output of the models or something, or the archive. Yeah, okay. And you talked about petabyte scale there. Do you have some examples of where you're actually seeing that right now? You know, the petabyte scale archival requirements from the models, or are you thinking that that's a near-term or medium-term or long-term result, you know, when say the models start to produce video more so, or images, or, you know, right now a lot of it's text output. The output seems to be kind of small, but yeah, just curious your thoughts on that.
Yeah, so I think multimodal models play a key role, like especially when you move towards videos, you know, the data sizes really kind of explode. But then there also, I mean, there's a thought about, you know, regulations. You know, companies will need to store data, you know, model data, but even maybe the steps, you know, during inference, you know, for liability reasons. And I'm sure, Curtis, you can talk even more about this, so feel free to add also your points.
I think you've hit the key point. You know, there's a lot of different artifacts that are generated from AI, and then there's a lot of needing to store the data that you used behind the creation of that AI models as well.
I was just going to expand on that a little bit, because there are some efforts underway, and I'm involved in them when I can be, on pushing for AI results to be auditable. So yeah, showing your work is important.
Yeah.
Anything else? Got about one more
If
minute.
there's time, I guess maybe I can ask a question back to the first person who asked a question. Wes is your name. Yep. Yeah. And I know that you're very active in the performance benchmarking effort for storage within ML Commons. Yep. So I wanted to, I guess, send your question back to you. So what do you see, I guess, in terms of the random access size, data sizes for random accesses, especially for inference?
So on inference side, I think we have an existing workload that most people have heard of and are familiar with, which is vector database for RAG. And we were trying to get this into this version of MLPerf storage, but it's not going to make it until the next one. But if you're using an on-disk index, so disk ANN with a normal database, and you're using normal size vectors, that is doing 4K random accesses to disk. I'm currently trying to find out if it will benefit from smaller than 4K. I don't know that answer. If anyone else is able to look at that and share it back with the community, that would be beneficial. The other workload that is starting to get talked about a lot and we're hoping to develop a benchmark for is going to be KV cache offload and migration. Even in that, I don't think that's necessarily going to be small IOs. The smallest granularity that is managed is going to be a block of tokens together at an individual layer level. So let's say 16 tokens for a single layer, that's going to be around 16 kilobytes, which isn't tiny. It's small, but it's not going to worry about saturating the IOPS on a device. So both of those workloads are smallish, but they don't get us to that smaller than 4K that I'm aware of. But they are latency sensitive, random, and small.
Okay. Yeah, thank you, Wes, for your insight.
Thanks, Eric.